equilibrium of concurrent forces. What is equilibrium? According to Newton's first law, equilibrium of a particle is said to be a particle is either at rest or in uniform motion. A particle is either at rest or in uniform motion. Okay? Here what he comes to say. That is, let's consider this particle as a stone or anything. This ball. Okay? This particle is at rest because all the forces that is acting upon this particle is equal in magnitude and opposite in direction. So they get cancelled each other because the normal force will be in this direction and the gravitational force due to its own weight is in downwards direction. Because of same magnitude but opposite direction, they get cancelled. So the net force, that is the resultant force, will be 0. Okay, that's what this equation states. That is, let's take there are so many forces acting on that particle, that is F1, F2 and F3. And the summation of these three forces should be 0 for a system or a particle to be in equilibrium. This is what equilibrium states. And let's see this example. Okay, here this is a simple pendulum example. Here the bob is connected to through a string to the wall. Okay, the tension due to the string is T in upwards direction, and the gravitational force due to the bob's weight is W, that is mg. You can take mg. Okay, these two forces will be equal in equal in magnitude but opposite in direction. So they get cancelled. Okay, and this bob is at rest and it's doing nothing. It's not moving. It's at rest. So this type of case is said to be static equilibrium because the object is not moving. It's in static position. Okay, so it's static equilibrium. And next one is this case. Here, the pendulum, the bob is moving in uniform motion. That is, it is going here and coming back here, and it will go in this position only. Every time here the bob goes from this position to here, it comes to this position and it will go on. At the end, it will be coming this position and it will be at rest. But the bob is moving at uniform speed. Okay, what we say, a particle is either at rest or in uniform motion. So it's in uniform motion, and the force due to string this tension is in upwards direction, and the gravitational force is in downward direction. Both gets cancelled due to Newton's law, that is equal in magnitude but opposite in direction. Okay, this case, this type of example is called translational equilibrium because here the object is moving with uniform speed. Okay, there is another type of equilibrium, that is rotational equilibrium. Rotational equilibrium. This case, the object will be moving or rotating with uniform angular velocity. Okay, here we see uniform speed. In this case, the object will be moving in uniform angular velocity. Okay, that case will be called as rotational equilibrium. Okay, and what is concurrent force? Concurrent force are a force that passes through a common point. Okay, they are force that passing through a common point in an object. This is the common point, and these forces are passing through the common point. Okay, and the net resultant should be 0 for equilibrium of concurrent forces. A force that is passing through the common point of an object and the resultant force of those forces should be 0. Okay, that is, let's see that the F1 is F1, F2 and F3 is passing through a common point. Okay, and these three forces are equal in magnitude and opposite in direction. That then the force will get 0 resultant force. Okay, if any one of these force has different magnitude or different in direction, then that force will make this object to move or rotate. Okay, that time the system is said to be unbalanced, or the system will not be in equilibrium state. Okay, when any one of these force have different magnitude, direction, the system gets rotated or moved. That time the system is not in equilibrium.
Previously, we have seen about equilibrium of concurrent forces and a small example, a simple pendulum, and what are the types of equilibrium. And now we are going to see about another example to this picture. In this picture, the two cranes are lifting a weight of 5 tons. The crane 1 is lifting the weight through its string, and the crane 2 is lifting as the same weight. The string has tension, that is T. For crane 1, the tension is T1, and for crane 2, the tension is T2. They are lifting the weight of 5 tons. The crane 1 string is inclined from the horizontal plane at an angle of 45 degree, and crane 2 is inclined at an angle of 30 degree. Okay. If any one of this force or tension is not balanced or changes, then the weight would get unbalanced and the total system will get collapsed. Okay, because the 45 degree and 30 degree are the balanced force that the crane should apply to the weight to keep the weight at equilibrium position. Okay, if either the angle or the force or the tension of the string gets varied, then the weight could get collapsed. It is the force diagram of that crane diagram. Here the force F1 is the tension of the string of crane C1, and force F2 is the tension of the crane C2. Here the angle is 30 degree for crane 2, which is inclined from the horizontal plane, and angle 45 degrees for crane 1, which is inclined from the horizontal plane. With reference to the horizontal plane, the angle is made. Okay, the 5 ton is the weight of the block, which is given in the diagram. This picture is example of concurrent forces. Here, this junction is used for the cable connections through which it passes through. Here the center of point is this, and there are so many cable connections going through this junction. The center of point is this, and all the forces of the cables are passing through this common point. You can see in this diagram. This is the red point, which is the center of force, and center of point, and all the forces are passing through this center point. We have already seen about concurrent forces that all the forces should pass through a common point of an object and the resultant force should be 0, so that the object will be balanced, else the object will move, right, or collapse. Here the center of point, all the forces are passing through the center of point and the resultant force is 0. Okay, we have already seen about equilibrium of concurrent forces. That is, concurrent forces, force that is acting or is passing through a common point of a particle. Okay, and we have seen its example. And what is equilibrium? Equilibrium means summation of force, that is force of F components, that is x, y and z components, should be 0. Okay, this is the condition for equilibrium. Now we are going to see problems on force that is acting on an equilibrium body or system. Okay, and this problem gives that information: a block of weight W. This is weight of the block is suspended from a rope tied to two other ropes at point P, and one rope is horizontally attached to the wall and the other one is fastened to the ceiling, and the angle between the ceiling and the rope is 6 degrees. What are the tensions in each of the ropes? Okay, and assume the weight of the ropes and the knot are negligible. That is, the weight and the knot of the rope are assumed to be negligible. If the weight of the block is 100 Newton, what is the tension in the ceiling rope? This is the question. The weight of the block is 100 Newton, which is the information given in this question. And now we are going to draw the force diagram based on this question. Here we have 3 ropes, and 3 ropes have 3 tensions. So here one rope is attached to the ceiling. Okay, one rope is attached to the ceiling at an angle of 60 degrees. Okay, this is the rope 1, and the tension that is acting in this rope is T1. Okay, and another rope is attached to the wall horizontally, and the tension that is acting to this rope is T2. Okay, it is horizontally attached to the wall, and another rope is connected to the block. Okay, another rope is connected to the block which has weight 100 Newton, and the tension that is acting in this rope is T3. Okay, this is the information given, and we have drawn the force diagram. Okay, here we are going to find the force tension of this system, that is the block and the third rope. Okay, now we are going to draw this system alone. This is the block which is 100 Newton in weight, and the gravitational force is in downwards direction, that is W, and the tension will be in upwards direction. Okay, because it's a normal force which pulls the weight against the gravitational force, and the gravitational force also pulls the block. So these two forces are equal and opposite in direction. Okay, and these two forces gets cancelled. Here there is no horizontal forces. Okay, that is summation of x fx is the horizontal force, and there is no horizontal force acting upon the system. So summation of fx is equal to 0, and there is a force that is acting upon vertically, that is summation of fy is equal to 0, which is a condition for a system in equilibrium. And here the two force that is acting vertically is equal in magnitude and opposite in direction, right? So these two forces are opposite in direction, and we can write like this: T3 is T3, right? T3 plus minus W, and we can get, that is the summation of forces were acting upon this system vertically, that is T3 plus minus W, because they are opposite in direction. Now T3 minus W, and here we have 0. So T3 is equal to W. This is what we get from this system, and let's take it as first equation. Okay, this is the first equation where T3 is the tension of the third rope that is connected to the block. This is the tension of the third rope that is connected to the block. And now we are going to find the tension of other two ropes. Now we are going to draw the force diagram. Okay, for the other two ropes. To find the tension, the force diagram is this. The T2 rope, which is fixed to the wall, is in this direction, and the T3 is in downwards direction, which is connected to the weight. Okay, and T1 is the tension of rope that is connected to the ceiling at 60-degree angle, and the vertical component of this T1 is T1 sine theta, which is theta is equal to 60 degree, and the horizontal component is T1 cos theta. Okay, now we are going to find the tension of the first rope, that is T1. Okay, here the vertical component is T1 sine theta, whereas the horizontal component is T1 cos theta. Here theta is equal to 60 degree. Okay, now the vertical component that is acting in this rope is T1 sine theta, and whereas the T3 is opposite in direction to the vertical component of first rope. So they are given like this. We have already known that summation of Fy is the vertical component equation, which is 0, and here the vertical components are T1 sine theta plus minus T3. Okay, so we get T1 sine theta is 60 degree, so sine 60 degree minus T3. Okay, here we substitute the value of T3, we get W. If the T3 go this side, then it will be positive, and according to this equation number 1, T3 is equal to W. So W is equal to T1 sine 60 degree, and sine 60 degree is equal to sine 60 degree is equal to 0.866. Okay, now we want to know the value for T1, not for W. So T1 is equal to 1 by sine 60 into W. Okay, so the value of sine 60 is 0.66. So 1 by 0.866 into W is equal to 1.155 W. This is for T1, which is equation number 2. Okay, the value for tension of the rope 1 is 1.155 W, that is weight. Okay, so this is the equation number 2, and this is only for Y component, and we are going to find for X component. Okay, now we are going to find the X component of T1, that is the tension of the rope 1. So what is the X component? It is T1 cos theta, and the X component has another force which is acting opposite to it, that is T2. So we have already known summation of Fx is equal to 0 because it's an horizontal component, and which is T1 cos theta plus minus T2. Okay, so we have 0 is equal to T1 cos 60 degree minus T2. Okay, and now for cos 60 degree we have 0.5 and we are going to find T2. What is T2? T1 cos 60 degree. We already have a value for T1, right, which is 1.155 W. So we are going to substitute that value in this T1, which is 1.155 W into what is cos 60, which is 0.5, right? So 0.5 into W into 1.155, we get 0.577 W, which is T2. This is equation number 3. Okay. Now we have value for T1, T2 and T3, which is the tension of rope 1, 2 and 3. We have find through this force diagram, and we have already know the value for W, which is 100. So we are going to substitute the 100 into the equation. Okay. So if we substitute the value for T1 will be 115.5 Newton. Okay, and the value for T2 will be 57.7 Newton. Okay, and the value for T3 will be 100 Newton. Okay, here in this question they have asked only the tension of rope 1. Okay, they are asking the tension of rope 1. So for this question the answer is this. The tension of rope 1 is 115.5 Newton. Okay, this is the example problem for a force that is acting on an object which is in equilibrium state. Okay.
Thank you for watching. Visit us at needbook.in.